Okay, so continuing on with our examples of differential equations. So we have now example number 2, which is a compound interest. So this is a classic compound interest. So suppose that we have a sum of money S sub O that is deposited at the bank that pays an annual rate of R. So the value S of T of the investment at any time T depends on the frequency with which the interest is compounded as well as on the interest rate. So assume that the compounding takes place continuously. So let's set up an initial value problem that describes the growth of our investment. So here is our investment. So basically, it's the value multiplied by the annual rate R. So this is the classic compounding interest problem. So let's try to use MATLAB with that one. Okay, so this is our differential equation. ds dt is equal to Rs with the initial condition of S sub O, where SO is the initial investment. So first, we have, sorry, we set up our variables. So unlike in our previous example, I had the variables one line at a time. You can actually do it multiple lines at a time. So again, a symbolic value, so symbolic variables. And then I had input it in our DE, our differential equation, put number 2 because this is example number 2. This to distinguish it from DE1 so that in any case, well, since it's a different file altogether, it should not affect one another. But anyway, just to be safe. So I have the E2 and the differential equation of S and T as a function of T R times S. And the initial condition is S sub O. That's the initial value. So I'll just simply run this section. Now this section just runs our initial value, which this section just runs, these are purely our inputs. So it just gives us our input. So I just to check then if our input is correct. And then we solve it. So again, we are using the solve. So this is the entry level among the solvers, differential equation solvers in MATLAB. So I had it at GSOL as a function of t. I input our equation and our initial condition. So just to double check our, okay, so here is what I was talking about. Our workspace is now full of values. So let me clear this workspace. Okay. And then run this one first again, just to be safe, because since I cleared our workspace, we don't have any values. So just run this section. And our workspace is now composed of our values R. Now we solve our differential equation. So run this section. So our equation is S of OE raised to RT. Now, case 1. So what if we have a withdrawals or deposits occurring at a constant rate of K? So it's just simply add a term K on our investment. So investment, the compounded interest plus additional investment on that one. So this is our equation. So we just put our term K. So again, run the same one. So I called it 2A because it's differential equation 2.1. So to speak. So run this section. So I just input the same value. So, but it gives me a whole new different values for our R. So here is our equation. Now, what if you have we have an individual retirement account open at age 25 with an annual investment of 20,000 deposit continuously. So this is like case number 1. So what is the rate of, if the rate of return is 8%, what will be the balance at age of 65? So we have our amounts. So basically, I did not put, have it as a differential equation because this is basically case number 1 with just values for our R and K. So our initial investment doesn't have, it's just you opened an account. And so you have initial investment at 0. So you have a rate of 8%, that's 0.08, and an investment of 2,000 per year. Sorry, not 20,000, it's 2,000 deposited continuously, so 2,000. And at the time of, from the age of 25 to 65. So T is not 65 nor is it 25. It's the difference between 65 and 25 because It's just basically the amount of time that the account is existing. So I input these values first. So and we have our actually this is solution. By the way, when you have the semicolon, it suppresses the output. So let me remove this one, and let me run it again. So okay, so when I remove this semicolon, it just showed the outputs. Okay, and then this is a solution to case one. So in here, rather than repeating this solution here, since I overwrote k's and t's. So if you look at k and t, it's no longer a symbolic function but has a numerical value. It's a double function. So it is a numerical value now because I overwrote the initial symbol value that I had written. So it's replaced by a double type of function, double type of variable, which is a numerical variable. So this is GSOL. This is still our value, but since I overwrote this one as a t, so this is g sol of t. However, what um what was returned to me is still a symbolic function because this is a symbolic function. So we should be using a different value that is subs here. But anyway, I had it on a different one. So I copied this equation again and got this balance of 588,000. So 5.88 E plus 0.5. So E plus 0.5, that means times 10 to the fifth power. So we have a 588,000, around 588,000 amount in the bank after 65. So anyway, that's the value here. So when we just substitute it simply as T, it just gives you it, which is t is equal to 40. It just replaces t with 40, but all the others, not necessarily. Okay, so this is, I think there's a different way to do this using subs, but I'm still working it out. Okay, now another example. So example number 3, this is, sorry, this is not a compound interest. So this is chemicals in a fund. Okay. So we have here a pond that initially contains 10 million gallons of fresh water. Now we have water containing undesirable chemical flowing to the pond at the rate of 5 million gallons per year. And the mixture in the pond flows out at the same rate. So like it's similar to the first problem where you have inflow and outflow but a steady state system. Well, steady state for the volume of water but not necessarily for the chemical. So water containing undesirable chemicals, so the concentration of the chemical is variable. So it is defined by a function gamma t. It varies periodically with time according to this expression. Gamma t is equal to 2 plus sine 2t grams per gallon. So what's the mathematical model for this process and determine the amount of chemical in the pond at any time? So it's like the first initial value here. So case 1 from this one. So just like how we did the previous one, so I had constructed this table so that it's better to visualize this one. So this is fresh water. So you have 0. This is 10 million gallons of fresh water. Now chemicals, I didn't, for brevity, I didn't copy the whole expression. I just put it as gamma T, grams per gallon. And the concentration now is Q. And just like the one before, this is Q over 10 grams per gallon times 5 million gallons per year. So this is grams per gallon. YT, so if we want it grams per year, we have it at 5 multiplied by gamma T. And then this is again another 5. Sorry, this is 5 million multiplied by, not 5, it's 5 million. 5 million gallons per year. Okay, so just like in the first example, it's rate in minus rate out. So 5 million gallons is 5 times 10 to the 6. So gamma T, 5 million gallons per year minus going out, it's 5 million times q over 10 million. 10 million is 10 raised to the 7th power. Now, simplifying this one, we have gamma t times 5 times to the 6 over. We can, 5 million minus, divided by 10 million is 1 half. So q over 2. However, the problem here is this one. It's quite a large value too. Really, it's quite problematic. So to further simplify it and remove this pesky 5 times 10 to the 6th power, let's have this variable q such that we can replace Q, the large Q, the concentration, as Q in terms of a million. So Q times 10 to the 6 to remove this pesky one. So I'll just remove, rather, substitute all large Q with a small q times 10 to the 6. So we have this one is Q times 10 to the 6th. And then this one is q times 10 to the 6. So all of the terms now has times 10 to the 6. And then cancel it out, all of them. And now we have this value. 5 times, let's change this, 5 times q gamma t q over 2, where our gamma t is 2 plus sine of t. Now, if you substitute it here, we have 5 times 2 sine of 2t over q2. So, if you use pen and paper, given this initial value condition, if you use pen and paper to solve this equation, rather you would have your equation as will be your resulting solution to this equation. 20, 40 cosine t and a half. Now, what if we use MATLAB using the dsolve function? This is ODE3. So let me clear first the workspace so that nothing, so all of these activities will be based on our equations, ODE. So again, this is our equation where gamma t is 2 plus sine t. So I just substitute the simplified version so that I don't have to introduce or name another variables gamma t. So we have here sims of qt and t. So we have here the variables q, t, and then q sub o. And then this is dE. So the differential equation of your equation. So this is the expression. And the initial condition at at q of 0. So I didn't put a q sub o unlike the first equation because we actually have a numerical value for the initial condition. It's not a variable value. It's a known value. You have 0 chemicals initially because your pad initially contains fresh water only. So running this one section, so I just have this initial condition and our equation. Now we solve it using dsolve. So if you use dsolve, you actually have a different equation from our the one we solved in pen and paper. So this is to show you that MATLAB has a different approach in solving differential equations compared to humans, and it tends to do approximations more so than the actual solution. So it's more of a numerical type of approximations rather than doing the actual solutions here. And however, if we plot it, since this is more of an approximation, so I just copied this equation and then substituted here from 0 to 20, so 20 years, and plotting it, we have this equation. Now, actually, this is an example from the book, and we do have the same answer value as the one in the book. So let's go back to our book. By the way, these examples are basically based on our reference book. So let me show you. I didn't put it here. So let us look at the one in Blackboard. Okay. This modeling. Waiting. Okay. See, this is the first value. We did reach the same plots as this one. Now here is the actual plot. So this is your solution, but and if you plot the actual solution, this one, you will end up with these values here. And our plot based on MATLAB is this one. So there are some um how should I say, ebb and flow, but it's not as pronounced as the one in the picture. But you can see here that when you have your at a certain time t, it's just like the first some example, certain time t, it becomes it oscillates around a certain value, which is 20, and this is what the value that we get also. It stays around this, it approaches 20 actually in a more linear function. It doesn't have oscillations, but it has a more linear function of 20. So it's a good approximation, but it's not the best. So this is for the desolve functions. So there are other functions in MATLAB, such as ODE45, which has a more accuracy in solving differential equations. And that will be the subject for the next part of our MATLAB exercises. But this is a general entry level solutions for now. So I'll be uploading this one in our Blackboard and as well as in the MATLAB course so that you can review this one. Okay, so that's it for now for our activity, or rather for this lecture. So I do suggest that you practice MATLAB with the solutions with the sample problems from the book in preparation for your applications, exams, and module 2, which should be the actual application.